Well, there, calculus folks. Hopefully you've had a chance to go through the investigation and get an idea about some of these shortcuts, and probably you are already developing ideas about some of these derivatives in chapter 1. But what we're wanting to do now is to pound through a bunch of examples and get used to this idea of taking the derivative quickly, not from first principles using the shortcut rules. So this page that you're looking at here on the smart board is on the back of the prerequisite skills, derivative shortcuts prerequisite skills sheets from the other week, Thursday or so. And so I'm going to get through these examples. It says apply the derivative rules to differentiate each function. Notice not from first principles like in chapter 1. So here we've got a function, and in function notation it's just x to the exponent 5. What does it mean to do? We just take the derivative, the 5 comes down in front, and the exponent goes down by 1. Done. That's it. That's the derivative. Notice that when it's in different forms, one thing that we'll want to do is change it into this form, and that was one of the skills we're talking about. So this one is better written as, well, the 1 sort of hangs out in front. X to the exponent minus 4, right, is how we could write it in this form with a negative exponent. Then I take the derivative of that. The negative 4 comes down in front, and I subtract 1 from the exponent, just like we're used to. And if I want to tidy that up a little bit so it looks more like the form that it was originally put in, then I'd go put x to the exponent 5 like that. Either of these are fine. This one, a little bit more difficult to see how I would write that in this sort of form, the easy to take the derivative form, derivative ready form, as I like to say. But what is it? It's t to the exponent something. The 3 is the root, the 2 is the exponent 2/3. And so that means when I want to take the derivative, and I'm going to mix up my notations here just so we're not used to just one. I'm going to use Leibniz notation here. So the derivative in Leibniz notation, the derivative of s with respect to t, basically that's the same as s prime or f prime at x. But the exponent comes down, I write down t, and then I subtract 1 off of the exponent. Now, you got to be careful. Watch your fractions here. This, I hope you can do in your head. Now, we don't necessarily like seeing it like that. The negative exponent means it should be in the denominator. And it's the cube root, right? And that would be it in tidied up form. All right. Next, constant and constant multiple rule. What does this mean? Well, that was another one of the rules we saw in our investigation, and essentially when it's a constant and we've taken the derivative of constant, well, it's 0, isn't it? Makes sense. What's the slope of a constant line? Well, it's 0. Here, when I've got a constant out front, essentially what I can do is I think of the constant hanging out front, then take the derivative of the x to the exponent 4. 4 comes down, the exponent goes down by 1, and then I'm going to tidy up here, right? Well, I got some fractions to work on. 12 over 7, x to the exponent 3, and that's f prime at x. Can I skip that step? Absolutely you can. Same as here. With the t in the denominator, change the form slightly. Watch my handwriting there. It's kind of messy. Did you know my handwriting's kind of messy? And then the derivative, and it doesn't matter what style you use. If you like the prime style there, or like this, you could write this as r prime at t, which might be better here. I'm trying to mix up my my notations, so we're not used to one versus the other. There'll be spots where we will use one over the other, but for now, I'm going to try and just mix them up. So I'm writing the 2/3 in front. The -2 comes in front of the t. Subtract 1 from the exponent, and then I got to tidy up. -4/3. And t to the exponent 3, I'll put the t to the exponent 3 in the denominator, and that's dr dt. How am I going to handle this? Well, the 2 is under the root. Doesn't look like we can write it in our nice, easy to take derivative form, but we can. I'm going to write it as the coefficient is √2, and then x to the exponent 1/2. Convince yourself that that's the same thing, and then now that when I take the derivative, that's when the y prime shows up. The 1/2 comes down. Subtract 1 from the exponent. -1/2, that's supposed to say. Excuse my writing. And then tidy up. The x to the exponent negative. I'm going to write this one more time so we can see that. The -1/2 means it's the x is in the denominator, and the half means there's a square root. And there's different ways to write the same thing if we wanted to, but I'm going to leave it like that and just keep going. Next, sum and difference rules. Essentially what this says, it says when I've got the sum or difference of a bunch of terms, that I can take the derivatives of the terms separate. So here, if I wanted to, and again, this is my notation just to get you used to more notation. You will be able to skip some of these steps. I'm going to take the derivative of this, and it's the derivative of each of these separate terms. And this is going to look strange, and normally we'd skip this step. This is kind of the derivative of each of the pieces is what we would think. We wouldn't necessarily write it, we'd think it. And so when we actually do that, it's the derivative of this piece is 3x squared. And pretty soon you're going to be combining rules. Like I'm going to do it right here. I know the 2 comes down, but the 5 gets multiplied by the 2. That's 10x, and the derivative of the constant part is just 0. So the derivative then, I'll write it as df dx, why not? Is 3x squared plus 10x, and the 0 I'm not even going to write down. There's other ones here that we don't have a rule for the product of two things, do I? So how am I going to handle this? Well, I'm going to do some work first. I'm going to expand this. So you multiply this out, and you get 2x squared plus 3x minus 5. And then I can take the derivative of each of the pieces, right? The 2 comes down, gets multiplied by this other 2, 4x. The 2 goes down to 1, and we can leave that off if we don't want to. Derivative of this is just 3. The x disappears because it goes from an exponent of 1 to an exponent of 0, and the constant term is gone. See? Pretty nice. And then the next one is a quotient. And later on we'll have a quotient rule, but now we can just divide the x into each of these pieces, and I've got, if I simplify this a little bit, this is kind of the skills that you're responsible for on the prerequisite skills. And then now the derivative of q with respect to x, and derivative of this, the 1 comes down, x to the exponent 1, the exponent goes down to x to the exponent 0. I'm just going to leave that. The constant term is gone, right? That's plus 0. I'll write that in, but we wouldn't normally. You could just leave that out. The -1 gets multiplied by this -1 to become +1. Convince yourself of that, and then subtract 1 from the exponent, x to the exponent minus 2. So when I simplify this, and if we wanted to, we could get a common denominator and simplify this further. And that depends entirely on the way we want to leave it. In the book, if you don't got the exact answer in the back of the book, you might need to change the form a little bit. Check with a neighbor. This one, 2x plus 3 to the exponent, or 2x plus 1 to the exponent 3, well, we're good at having and taking derivatives of this, so we need to make that look like that. Well, multiply it all out. Some of you that've got a wicked memory might remember how to use the binomial theorem to multiply this out. The rest of us would just have to multiply it out, and I'm just going to save us a little bit of time and write this as 8x cubed plus 12x squared plus 6x plus 1. And then now we've got a sum of all these things, and we're starting to get good at this now. Take the derivative, is the derivative of each of the pieces, right? The 3 comes down, gets multiplied by the 8, that's 24. X squared plus 24 x to the exponent 1 plus 6, and the constant term's gone. Lovely. And it gets worse or better or interesting or harder or whatever you want to say. Again, the idea is get these terms, whip them into shape so I can take the derivative of them. Right? Well, this is negative 3. The 2 has the exponent 4 on it. 2 to the exponent 4 is 16. X to the exponent 4. See, I can take the derivative of this. That's not bad. This is a mess, right? If I write, divide that term into both of those terms, negative 1/3. And I'm going to spend a line here figuring out what this last term is, because square root of x is x to the exponent half. The square root, oh, hang on, did I goofed that up? This is supposed to be 3 halves, right? This on the bottom here is x to the exponent 3 over 2 on the bottom, right? And so if I write that on the top with the 4, it should be negative x to the exponent 3 halves. So on the bottom here I have 3 halves, and then 2 exponents divided, so I subtract them. I'm not going to take the derivative yet, working on it. This first term's ready to take the derivative, but I got to do it all at once. The second term's ready for the derivative, but I got to do it all at once. Subtract these exponents. What's a half? No, I don't have any margin here. A half subtract 3 halves. A half subtract 3 halves is 1, isn't it? Negative 1. So this becomes plus x to the exponent minus 1. And now I'm ready to take the derivative. G prime at x. The 4 comes down, gets multiplied out front. I'll simplify this next step. Same as here, I'm writing the 4 out front. The negative 3 halves gets written, subtract 1 from that, right? Subtract 1 is subtract 2 over 2, right? So this is negative 5 halves. And that's the derivative of that term. This one, the minus 1, comes down in front, and I subtract 1 from the exponent. And now I'm going to tidy up this derivative. Negative 12 over 16. See, I can see that. I'm going to simplify that as well. X to the exponent 3 minus 12 over 2 x to the exponent negative 5 halves minus x to the exponent minus 2. often in the book, what they'll do is they'll have all of the powers with positive exponents. So they'll put all these negative exponents in the bottom. I think I'm okay with this. We'll leave this, but I'm going to tidy up one more step here. Divide 4, the lowest terms, 3/4 x cubed minus 6 x to the negative 5/2. You could write negative 2.5, and then finally x to the exponent minus 2. Phew, pretty good. Look at, there's the one that we just did. And where do we start this lesson? We started this lesson with taking the derivative of x to the exponent 5, and that's what we ended up with, all in one period. So that's pretty good. If we have time, we'll get on to the second part, which is the derivatives and tangents together. There'll be another video for that coming up shortly if there's time.